Have you ever stopped to think about the hidden rules that run our entire world? I'm not talking about traffic laws. I mean the deep quantum rules that decide why your shirt is blue, or why a neon sign glows, or even how stars shine across the universe. Well, today, we're going to pull back the curtain on these rules and decode the secrets of electronic transitions. It really all comes down to this, doesn't it? It feels like a simple childhood question, but the answer is buried deep in quantum physics. It's all about how the tiniest particles inside an atom behave. And you can think of it as them having a choice. Do they take the fast lane, or do they take a secret back alley staircase?
All right, so to get this, we've got to zoom way in, right down to the home of our star player for today, the electron. See, inside every single atom, electrons are buzzing around, but they're in very specific places. They're not allowed to be just anywhere they want.
Let's use an analogy. Imagine an atom is like a giant skyscraper. Each floor represents a different energy level, and our electron is a resident living there. It can live on the first floor, or maybe the 50th, but here's the key. It can never ever just float between floors. It has to be on one level or another. So how does our little electron move up in the world? Well, it needs a burst of energy. Imagine a tiny particle of light, a photon, comes along and zaps the building. That photon gives the electron just the right amount of energy to instantly ride an elevator up to a higher floor. This new high-energy apartment is what we call the excited state. But here's the thing. What goes up must come down, right? Being in that fancy, excited state is only temporary. The electron wants to get back home to its cozy ground floor, and the most common way to do that is to take the express elevator straight back down. This express route is what physicists call an allowed transition. It's the superhighway, the most common, high-probability path that follows all the standard quantum rules. And as that electron drops back down, it has to get rid of its extra energy. How? By spitting out a new photon of light. And how fast does this all happen? We're talking about 1 nanosecond. That's a billionth of a second. It's basically instantaneous. You could blink your eye, and this would have happened a billion times over. It's just mind-bogglingly fast.
So think about it. When you look at a red stop sign, what you're actually seeing are trillions upon trillions of electrons absorbing all the colors from sunlight except for red. They get excited, then they instantly drop back down, firing off red photons in this super fast, allowed way. That constant, rapid-fire process is what our brains see as a solid, stable color.
But what happens if that express elevator is out of service? What if the quantum rules actually block the direct path down? Well, our electron has to find another way home, and that way is the secret, slow, and rarely used emergency staircase. And this brings us to the forbidden transition. Now, forbidden sounds pretty dramatic, doesn't it? But it's not truly impossible. It just means that this particular path kind of bends some of the quantum rules, which makes it incredibly unlikely to happen. So the electron gets stuck up there in its excited state, just waiting, sometimes for a long time, for that 1 in a million chance to finally take the slow way down. So let's just put these two paths side by side so you can really see the difference. The allowed path, the fast lane, that's high probability, happens in nanoseconds, and it follows all the rules. The forbidden path is the complete opposite. It's a super low probability, it's incredibly slow, we're talking seconds or sometimes even longer, and it only happens by bending the rules. Okay, if you remember only one thing from this whole explainer, make it this. Fast transitions create color. Slow transitions create a lasting glow. The lightning-fast, allowed transitions give us all the stable, everyday colors we see around us. But those slow, improbable, forbidden ones, they give us the magical world of things that glow. So this is all a really neat bit of physics, but you might be thinking, why does this actually matter? Well, it matters because understanding and controlling these two different paths, the fast one and the slow one, is absolutely fundamental to the technology that powers our entire modern world. And now we can finally solve our mystery from the beginning. That red stop sign is red because of constant, instantaneous allowed transitions. And that glow-in-the-dark star in your ceiling? It glows because of the slow, forbidden ones. It soaks up light all day, trapping its electrons in that excited state. Then, all night long, those electrons slowly, one by one, take the forbidden path down, releasing photons that create that amazing, lasting glow. And you know, this isn't just about color and toys. Manipulating these transitions is exactly how we create super efficient LEDs. It's the secret behind how lasers work.
You're basically forcing a huge number of electrons to take the same path down at the exact same time. It's crucial for building better solar cells, for advanced medical imaging, and even for astronomers trying to figure out what distant stars and nebulae are made of by analyzing the forbidden light they send out.
It really is amazing when you think about it. Something that's supposedly forbidden by the rules of physics turns out to be one of the most useful tools we have. By learning how to harness the universe's most unlikely pathways, we've literally built the modern world. It really makes you wonder, doesn't it, what other quantum secrets are out there, just waiting for us to find them?